All right, today we're diving into one of the biggest puzzles in all of astrophysics. It's a fundamental mystery about the very fabric of our universe, and it starts with a surprisingly simple question.
So, we've known for about 100 years now that the universe is expanding. Simple enough, right? But here's the kicker. When we ask how fast exactly, our two best ways of measuring it give us two different answers. And that contradiction, well, that's one of the biggest headaches in cosmology today.
And let me be clear, this isn't just some small rounding error. It's a major, nagging disagreement that scientists call the Hubble tension. And it's a really big deal because it suggests our standard model of cosmology, the rule book for how we think the universe works, might have a whole chapter missing.
To really get a grip on this tension, we need to look at the two conflicting pieces of evidence. Think of it like a cosmic case file with two star witnesses, and they're both telling very different stories.
Okay, so on one hand, we've got method one, which is kind of like looking at the universe's baby picture. Scientists look deep into the cosmic microwave background. That's the leftover heat from the Big Bang. This picture tells us how fast the universe should be expanding today. Then you've got method two, which is more direct. It's like using cosmic mile markers. Astronomers look at things like exploding stars in the modern universe to calculate the expansion rate right now. And right here, this is the heart of the whole problem. The baby picture method predicts an expansion speed of about 67 kilometers per second for every megaparsec of distance. But the cosmic mile markers give us a faster rate, around 73. Now you might think, hey, that's pretty close. But in cosmology, that gap is a canyon. Statistically speaking, these results just do not agree. And this is that baby picture we've been talking about. I mean, just look at it. This is a snapshot of the entire universe when it was only 380,000 years old. Those tiny little fluctuations in color are differences in temperature, and hidden inside that data is the calculation that points to that slower expansion rate. It's beautiful, but it's also the source of our puzzle. So the bottom line is the evidence from the early universe and the modern universe just doesn't line up. And that discrepancy has sent scientists on a hunt for new explanation, some missing ingredient in our cosmic recipe. And a new suspect has entered the scene, one that's totally invisible and as old as time itself. This potential solution might be something called primordial magnetic fields. Now stick with me here. The idea is that these incredibly weak but absolutely enormous magnetic fields could have popped into existence in the fiery chaos right after the Big Bang, stretching across the entire cosmos. What if these ancient invisible fields are the missing piece we've been looking for? This image does a great job of capturing the vibe of what we're talking about. The early universe was just this chaotic, incredibly energetic soup of particles and energy. So it actually makes sense that a fundamental force like magnetism, born right in that primordial soup, could have subtly nudged the whole course of cosmic history from day one. Okay, but wait a second. How on earth could a faint magnetic field from billions of years ago solve a problem we're taking today? Well, the connection is surprisingly clever, and it all goes back to one critical moment in the universe's very first chapter. It works kind of like this. First, you have to picture the very early universe as this dense, hot, opaque fog. Light couldn't travel through it. For the universe to become transparent so light could travel freely, protons and electrons had to combine and form hydrogen atoms. Now, here's the key part. These primordial magnetic fields would have given that process a tiny little nudge, slightly changing when and how that happened. And that tiny change billions of years ago would alter the baby picture, the CMB, just enough to perfectly account for the discrepancy we see today. So is this just a neat idea, or is there any actual evidence to back it up? Well, that's the exciting part. Scientists are putting this theory to the test right now. A recent study published in a major journal did exactly that. Researchers used these incredibly powerful three-dimensional computer simulations to basically rebuild the early universe inside a computer and see how these magnetic fields would have actually behaved. And the results are pretty amazing. The simulations confirmed that, yes, these fields could totally resolve the Hubble tension. It works! And what's really cool is the strength they would need to be between 5 and 10 picogauss, which is unbelievably weak. We're talking a quadrillion times weaker than a fridge magnet. That makes the whole idea feel really plausible. Of course, the next big step is finding direct observational proof. And for that, we're going to need even more precise instruments. And this is why this matters so much. I mean, sure, it would solve the Hubble tension, which is great, but it's bigger than that. If we can prove these fields are real, it opens up a whole new window into the physics of the universe's first few moments. It's like getting a brand new tool to study the Big Bang itself.
It really is an elegant solution to a really complex problem, isn't it? It's a great reminder that the answers to some of the biggest questions we have today might just be hiding in the faintest whispers from the dawn of time. And that just leaves you wondering, what other secrets from those first moments are still out there, just waiting for us to find them?